So here we have part 2 of B3, and it's dealing with electric and gravitational fields. So here I have, it's actually from topic 6, fields and forces, and we're going to have two different types of fields we can look at. We've got our gravitational fields and we've got our electric fields, and as you can see the formulas that relate them are pretty similar, and we're going to use them. I think that's fine for the moment. So state in terms of electrons the difference between a conductor and an insulator. So with a conductor, you have electrons that are free to move. So free to move. These are usually what we call our valence electrons, our outer energy shell electrons. And when an electric field is placed on this conductor, these electrons actually move. Where an insulator, there are for an insulator, these electrons are not free to move. So it's pretty straightforward. Suggests why there must be an electric field inside a current carrying conductor. Okay, so we've got it. This is 3 marks. So this is actually quite an extensive question, and we can actually use this formula in it. So to have an electric current, a current implies that the electrons are moving. So to get them moving, there has to be a force. There needs to be a force to cause them to move. Sorry, I don't know what's happening with my pen here. To cause the electrons to move. To cause the electrons to move. I don't think I should write. It's to move. Something's happening wrong with my pen. I'm not sure what's going on with it. Anyway, let me just speak perhaps. And that comes from here, because force is equal to E times Q. So this is the electric field, and when it acts on a charge, an electron for instance, it will have a force, and that will cause it to accelerate, to move. So the magnitude of the electric field inside a conductor is 55 newtons per coulomb. Calculate the force on a free electron in the current. So we're going to use that formula as we got there. We've got force equals E times Q. This is my E, so this is 55. My computer's going so slowly. And the Q is 1.6 times 10 to the negative 19. And when I work that out, I think it comes to something like 8.8 times 10 to the negative 18 newtons. So as you can see, this is an extremely small force, but remember the mass of an electron is something like 10 to the minus 31 kilograms. So although it's a small force, it actually exerts quite a big force for the size of the particle. Then looking at this one over here, the electric force between 2-point charge is a fundamental force, as is the gravitational force between 2-point masses. State one similarity between these two forces and one difference, other than the fact that the one applies to charge and the other to mass. So these are our two formulas actually here. Let me just tidy things up here. This is my for gravitational force, and this is for my electric force. So as you can see, the similarity is that both forces are proportional to 1 over r squared. That's in both of them. You see this? 1 over r squared, 1 over r squared. We have the products of the masses, the product of the charges. And the difference between them is that for gravity, it's only attractive. And it's actually extremely small, very small. Where for your electric field, it can be both attractive and repulsive. And comparatively, it's large. It's many orders greater than your gravitational force. Fine. So let's go on to the next page here, and we have a question here where it says the force on a mass of 1 kilogram falling freely near the surface of Jupiter is 25 newtons. The radius of Jupiter is 7 times 10 to the 7 meters. State the value of the magnitude of the gravitational field strength at the surface of Jupiter. So we have got here that it is going to be 25 newtons per kilogram. That will be the gravitational field strength. As we, for 1 kilogram, for the Earth, it's 9.8 meters per second to the minus 2, and we've got it here also for Jupiter. Because it's 25 newtons, it would be 25 meters per second to the minus 2, or we could use the unit 25 newtons per kilogram. And then calculate the mass of Jupiter is this value over here. So we're going to use this formula over here, that G is equal to force over mass, and when we put it into the formula we're going to get big G, and this will be the mass of Jupiter divided by the r squared, and we know that this is 25, and so we need to put this in. Now this value over here, this is our constant value. Now if I just go, I'm going to have to lose all of this, I'm afraid, but I just want to go and show you that it's where this is, where you find this. It's this one over here, 6.67 times 10 to the negative 11. So we better go back to where we were. So we're going to have remember we've got our here that G, which is our field strength, gravitational field strength, is big G, the mass of Jupiter, divided by r squared. So the mass is equal to G r squared divided by big G here. So this is 25 times by our r squared, which is 7 times 10 to the 7, and we're going to square that, and we're going to divide that by our 6.67 times 10 to the negative 11, and we're going to get something like, I think, 1.8. Hopefully this will work out, times 10 to the 27 kilograms when you do that. Alright, so that's just that question over there.